So now we come to the next part of the lecture, which I think is one of the most interesting applications of Fourier series, and that's using Fourier series to solve separable partial differential equations. So suppose that we want to solve the heat equation, specifically the 1D heat equation. Or the temperature function along a one-dimensional bar. We've seen before that this is the equation k times du squared, the second derivative of temperature with respect to position, is equal to du dt. Where k could in general be a function of either temperature or position or time, but we're going to assume that k is constant. This is called thermal diffusivity of the medium. So the partial differential equation here is this heat equation. And we actually have to always specify certain boundary conditions. So we'll say that the bar goes from 0 to some length b, and the boundary conditions are actually what are going to make this a separable differential equation. And there are many different types of boundary conditions that we could put on this problem, but the easiest boundary conditions are having a 0 boundary condition on the left-hand side of the bar, so 0 temperature on the left-hand side of the bar, and the temperature of 0 at B as well for all times t. There are many other boundary conditions that can be put on the bar. Some will result in more simple boundary conditions will result in solution via Fourier series, this separable PDE. However, some boundary conditions, if they're complicated, require a little bit more intense analysis. We also have initial conditions as well, which means that at time t0, t not equals 0, the initial temperature distribution will be some function f of x. So I'll go through and show how to solve this PDE using the method of separation of variables, which relies heavily on the boundary conditions of this problem, and on the idea of Fourier series analysis. So suppose that we can find a solution of the form u of xt is equal to some function of x times some function of t. And this is sometimes called an ansatz. So we're going to look and see if we can find a solution of this form. And it turns out that if we can find solutions of this form for linear partial differential equation, we can collect all of the solutions of this form and add them together and get the true general solution to this problem because of the linearity of this partial differential equation right here. So what we're going to do is start by looking for solutions of this form and see what that's going to imply about the solution. And so we'll determine the PDE star, and we're going to substitute this assumption, or this ansatz, into star and see what that implies about a separable solution of the PDE. When we do this, we get the equation k times the second derivative of x, which is a function of x, times capital T, which is only a function of t, has to be equal to the t partial derivative of x times capital T and because x is a function of x, a single variable function of x, and capital T is a single variable function of t, this reduces to k times x double prime times t is equal to x times t prime. And you might ask, well, what is this really doing for us? Because this seems to be complexifying things, but we have some real magic that happens here if we rewrite this equation. Right? If this equation is to hold, then x double prime divided by x will have to be equal to capital T prime over t times k. And we want to pause for a moment and take a look at what we have here. The left-hand side of this equation is a single variable function of x. And the right-hand side of this equation is a single variable function of t. And I want you to think for a little bit about what this implies, but what it implies is something very special. If you have that a single variable function of x is equal to, specifically a ratio of two single variable functions of x is equal to a ratio of two single variable functions of t only, the only way of having this be true is if both sides or both ratios are equal to some constant value. Neither of these ratios can be functions of either of the variables, otherwise what we have here would not be possible to do or satisfy, so we wouldn't be able to satisfy this equation. And this is really the key thing to note when we're looking at this separability, means that this entire, both of these expressions have to be equal to some constant c, which we'll actually solve for and figure out exactly what values it can take on, which is why this constant c is sometimes called the separation constant. Of the boundary value problem. This PDE coupled with whatever boundary conditions and initial conditions you have is called a boundary value problem. And what's really nice here is that because each of these two equations have to be equal to the same constant c, then we get a second order differential equation that has to be satisfied in x. And a first order differential equation that has to be satisfied by the function t. And this is really special because what we've effectively done by assuming this ansatz is shown that any separable solution to this this PDE here has to satisfy, well, the x function has to satisfy this second order ODE and the t function, capital T, for the heat equation in order to satisfy this. If it's separable, has to satisfy this first order differential equation. So what we've essentially done is taken our partial differential equation and converted it for a separable solution into two ordinary differential equations, which should be more familiar to solve. And this is really the heart of this method. So this first order differential equation is just the exponential equation, and it has the general solution for any initial temperature of T naught times e to the kc times T. And this is a general solution that's valid regardless of what the sign of C is, if C is negative or positive. this will still be the same solution. However, this requires a little bit more of an investigation. Specifically, we have to look at what the if we get physical solutions for given boundary values. Remember, the boundary conditions here for a separable solution will need to be satisfied by the solutions of this ordinary differential equation, and the boundary conditions then reduce for the separable equation to x of 0 times t of t equals 0, and the second boundary condition will be satisfied if x of b times capital T of t is equal to 0. And these have to be true for all values of t. So what this means is that we actually have to put on specific boundary conditions onto x. And it's this step where things become a little bit more difficult if the boundary conditions are more complicated. It's still possible in many cases to do separation of variables with more complicated boundary conditions. However, you do need to be careful at this step when you're solving for x. So when you're solving for this differential equation right here. But we're choosing to go over the simplest possible scenario now just to kind of get the idea down. And it's important to point out that mathematically this is called a Sturm-Liouville problem, or a problem of Sturm-Liouville type, where we have this second order linear inhomogeneous ODE with specific boundary conditions that have to be satisfied. And the theory of Sturm-Liouville problems is very, very intimately related with what we're doing here and whether or not we can solve a given partial differential equation using the method of separation of variables. So I encourage you to read further into that if you're interested. But just kind of going over the general idea here, we have three different possible values for C. The first possible value for C is C positive, in which case the solution to this differential equation in general will be x of x is equal to some constant d1 times hyperbolic cosine of the square root of the absolute value of c times x plus some constant d2 times hyperbolic sine of the square root of the absolute value of c times x. And these can be written in terms of exponentials, the positive and negative exponentials as well. However, for applying the boundary conditions here, hyperbolic cosine and hyperbolic sine are a little bit easier to see what's going on, because if we go through and try to solve for our constants d1 and d2, when we plug in 0 here, we get that this is going to be d1 times 1 plus d2 times 0, and this has to be equal to 0 to satisfy our boundary condition, which implies that d1 is equal to 0. And so when we go to satisfy our other boundary condition at b, this becomes d2 times hyperbolic sine of the square root of the absolute value of c times d has to be equal to 0. And the only way of satisfying this boundary condition is, again, making d2 equal 0. Because the only place that the hyperbolic sine is 0 is when d is 0, and that would be the length of the bar is 0. So this case is no good. Or I should say the case C positive is no good because there are no non-trivial solutions. Right? There are no solutions to this partial differential equation that are separable, where this C value is strictly positive. We can go through and do this exact same thing for C equals 0. And when C equals 0, the general solution x as a function of x is going to be some d1 times x plus some constant d2. And again, when we go to satisfy our boundary conditions, x of 0 is just d2, which implies d2 would have to equal 0. And x at d, because the length of the bar, will be v1 times d, and x, or d2 is 0, so the only way of making this equal to 0 is, again, if d1 and d2 are both equal to 0, just like in the previous case. So again, there are no non-trivial or non-zero solutions to the boundary value problem here that are separable and that satisfy these boundary conditions with C equal to 0. And so the last hope here is that we can find a class of non-zero or non-trivial solutions for C less than 0. Specifically, we'll take C equal to negative omega squared and try and see if we can figure out what omega is. So remember, in the case C positive, you get the differential equation x double prime minus absolute value of C times x equals 0. In the case of C equals 0, you get the differential equation x double prime is equal to 0, which is where this solution right here is coming from. And in the case of C negative, we have the differential equation x double prime plus omega squared times x is equal to 0. And I'll use omega squared up here as well, just to be specific. And when we go through and solve this, the solution to this second order differential equation is going to be of the form a times cosine of omega times x plus b times sine of omega times x. Where a and b are constants, and we have to satisfy the boundary conditions. x of 0 is cosine of 0, which is 1, so a times 1 plus b times 0 has to be equal to 0. So a is 0 will satisfy this boundary condition. And things aren't looking too good, but sure enough, we get that some magic happens when we go to apply the boundary condition at b. X of b is going to be b times sine of omega times b, which has to equal 0. And sure enough, there are infinitely many possible solutions to this equation right here. Specifically, like for any value omega, where omega is equal to n times pi over b, n is equal to 0, plus or minus 1, plus or minus 2, and so on and so forth, we have a solution to our equation. And I want to note that the negatives are non-physical. Which is why we can take the following step. So we have infinitely many possible solutions here to our this Sturm-Liouville problem with C negative. So the general solution then, in terms of n, is un of x comma t is equal to x n of x times t n of t, which is bn times sine of n pi over b times x times t naught n e to the negative omega n times k omega n squared times k times t, which I'll abbreviate for the constant. Right? T naught here is an arbitrary constant, depends on initial condition. Same thing with bn, so I'll just abbreviate this entire thing as lowercase bn. And this is where the real magic happens. Because we have that this is satisfied, or n from 1 to 0. At 0, when n is 0, this is 0. So 1, 2, 3, and any positive natural number of n are the solutions that we have here. And so the general solution then is the sum of all of these separable solutions. And as long as this series is uniformly convergent, which we can very easily show that it will be uniformly convergent for a certain class of initial conditions, we have that this infinite summation is the general solution to this partial differential equation, because we have that if this is a uniformly convergent series, we can do term-by-term differentiation, and this infinite series will go ahead and satisfy this partial differential equation. So the only thing that we have left to do here is to satisfy our general initial condition, and sure enough, we have a distinct way of going through and satisfying our initial condition. The initial condition here is u at x, 0 equals 0 is the summation from n equals 1 to infinity of bn times e to the 0, which is 1, times sine of omega n times x, or, if you will, the summation from n equals 1 to infinity of bn times sine of n pi over b times x. And the initial condition has to be the function f of x, whatever this is. And based on our previous work, we recognize this immediately as the Fourier sine series, or the Fourier sine series being the odd Fourier extension of f of x. So the Fourier series that converges to f of x on the interval from 0 to b. So we know immediately how to go through and calculate these coefficients Bn using our orthogonality relations. Specifically, Bn is going to end up being 2 over b, where b is the length of this interval, times the integral from 0 to the end of the interval of f of x times sine of n pi over b times x dx. Right, and there you have it. Right, this now gives us the Fourier series solution to our heat equation problem for any initial condition where the Fourier sine series is a valid series. And sure enough, any initial condition that you can think of, piecewise, continuous, nice function f of x, will give you a convergent, uniformly convergent Fourier sine series. So this is very, very, very cool, very, very, very incredible. I'll just do one specific example here. And this is relevant to the homework problem, and that is, let's go through and do this for the specific initial condition u of x naught, or f of x, is equal to x on the interval from 0 to b over 2 and from b over 2 to b the function L, or a b minus x. And so for this problem, Bn is going to be 2 over b times the integral from 0 to b of f of x times sine of n pi over b times x which is 2 over b times the integral from 0 to b of x, or b over 2, of x times sine of n pi over b times x dx, plus the integral from b over 2 to b of b minus x times sine of n pi over b times x dx, using the fact that the definite integral can be split into sum for piecewise functions like this. And when we go through and use integration by parts on each one of these integrals, we end up getting that Bn will be 2 over b times b over n squared pi squared times b sine of n pi over 2 minus n b pi over 2 times cosine of n pi over 2. That's this first integral right here. And the second integral that we get is the b squared over n squared pi squared multiplied by sine of n pi over 2 plus n pi times cosine. Let me make a little bit more space here. N pi over 2 over 2. So we have a little bit of a cancellation here. You can factor out the b squared over n squared pi squared. It's to be 2 times b. You have b squared over n squared pi squared here. And this will be times sine of n pi over 2 plus sine of n pi over 2 gives you 2 times sine of n pi over 2. And here you have minus n pi over 2 cosine of n pi over 2. And then from this term right here you have plus n pi over 2 times cosine of n pi over 2. These two terms actually cancel one another. We're just left with the simplified equation 4b over n squared pi squared times sine of n pi over 2. So the general solution for the heat equation with these specific boundary conditions and initial conditions is this infinite sum with this specific Bn function, or explicitly if we plug in b4b over n squared pi squared times sine of n pi over 2 times e to the negative n pi over b squared times k here. A little typo here, we should have k right up here. This infinite sum is the solution to the general solution to the heat equation that satisfies this initial condition and the boundary conditions talked about before. And let me fix this right here as well, because there should be k. So if you want to go through and plot this for various values of time, I recommend going through and doing this using Desmos or Python. I wrote my own custom Python code to actually give me an animation of this for various values of t. And the downside of using this in code is that you have to you can only do the finite sum, so you can only plot out for a finite n finitely many terms of this Fourier series expansion. Or it's this sum not from 1 to infinity, but from 1 to n. That being said, if your coefficients are nice enough, you'll have good convergence. If you don't have nice convergence, or you don't have fast convergence, you'll have to use more sums, more terms in your sum, which will result in maybe possibly artifacts. So like the Gibbs phenomena at any discontinuities. It's not as much of an issue with the heat equation, but we will see that when we plot out our solution to the wave equation with discontinuous or a poorly chosen initial condition. However, this does sum, it converges to the exact solution as n goes to infinity. So let's take a look at this right now. And here I have a Desmos screen, but I'll open up my solution to the heat equation. And this is the initial condition in blue with evolving solution to the heat equation in time with fixed endpoints at 0. You see that very clearly this is what you would expect for a heat problem, a sort of smoothing of your initial condition, and this is really quite incredible that this works out so nicely, and it works out so nicely for so many very basic separable partial differential equations. So we aren't limited to only the 1D heat equation. We can do this with the 2D heat equation, with the 1D wave equation, the 2D wave equation, the 1D potential equation, the 2D potential equation, and even the 3D versions of each one of these equations as well. This is very incredible. So let's see an example of extending this process to the heat equation 2D, and we'll take a look at this and see what the differences are, and we'll actually see how similar this is in 2D. So the constant coefficient heat equation in 2D is K times the second derivative of temperature with respect to X plus the second derivative of temperature U with respect to Y is equal to the derivative of a U with respect to T, where U is a function of X, Y, and T. So this is the partial differential equation, and again, in order to have this be solvable as a separable partial differential equation, or in order for this to be a separable PDE, we have to have certain boundary conditions. Now, these are not the only boundary conditions that give you a separable PDE, but the easiest boundary conditions to take are 0 on the boundary points, just like before. And in a little bit, I'll show how to do the wave equation with slightly different boundary conditions. So for the 2D heat equation, we'll take the boundary conditions to be 0 at both boundaries. With the PDE being over the finite domain, from 0 to B in X, and from 0 to C in Y. So we need 4 separate boundary conditions on each one of these boundaries, and our initial condition is going to be U at t equals 0 is equal to some function f of x, y. And just like before, we start with step 1, which is the ansatz of looking for solutions that are separable, or of the form of a function of x times a function of y times a function of t. But things will be a little bit more complicated now, because when we plug this substitution into our partial differential equation, we get k times x prime prime times y times t plus x times y prime prime times t is equal to x times y times t prime. which is a little bit more complicated than the 1D case. However, we can still go through and simplify this. The first thing that I recommend doing is dividing by x times y times t to get k times x prime prime over x plus y prime prime over y is equal to t prime over t. Which is in fact the same thing if we rewrite this a little bit as x prime prime over x is equal to t prime over t times k minus y prime prime over y, which, just like before, is a ratio of function of only x here and this entire thing is function, and it's also a ratio function of y and of t. For the same reason as before, we have to conclude that this is going to be equal to some constant negative lambda. Which gives you two separate equations that have to be satisfied. X prime prime over x is equal to negative lambda, and this function right here is equal to negative lambda. Which we can again say, because this is a function of ratio function of only t, and this is a ratio that's a function of only y, that this entire thing has to be equal to, or t prime over k times t plus lambda has to be equal to y prime prime over y, because this is a function of only t and this is a function of only y, this has to be equal to negative mu, where negative mu is another separation constant. And just like before, this now gives us three separate differential equations that we have to solve for x prime prime minus lambda times x is equal to 0, y prime prime, plus lambda times x equals 0, y prime prime plus mu times y is equal to 0, and t prime plus k times lambda plus mu times t is equal to 0. And just like before in the 1D case, we can go through and solve these. First off, we know that t of t will be equal to t naught times e to the negative k lambda plus mu times t and we can also go through a similar procedure to the 1D case to solve both of these differential equations and satisfy the relevant boundary conditions, the relevant Sturm-Liouville problem for each one of the differential equations here. And when we do that, specifically we get that x of x, or I should say x m of x is equal to some constant a star m times sine of m pi over b times x. And likewise, you can go through and show that the only non-trivial solutions for y, the solution is yn of y equal to some constant a cross n sine of n pi over c times y. Where an only non-trivial lambda that satisfy this are lambda equals lambda m, which is m pi over b squared, and mu equals mu n, which is n pi over c squared. The procedure is almost exactly the same to the previous example that I went through and did when we went through and solved for the boundary conditions and showed that there are no non-trivial solutions for these specific boundary conditions, only when c is a specific value of that depends on n. This means that t in general will be a function of t and it will be indexed by m and n. Specifically, it'll be t mn, where tmn naught is, times e to the negative k times m pi over b squared plus n pi over c squared times t. And so then for every m value, or m equals 0, And 0 we don't even really care about because the sign of 0 is 0, so m equals 1, 2, 3, and so on and so forth. And for every n value, we have a solution that's separable of the form umn of x, y, t is equal to this function times this function times this function multiplied by some arbitrary constant a m n. And any solution of this form satisfies both boundary conditions that we initially put on the problem. And by the linearity of this PDE, the most general solution then is going to be the sum over all m and all n of this expression right here. Specifically, u of x, y, t is going to be a double summation n from 1 to infinity, m from 1 to infinity of this expression right here. And at first this might look a little bit daunting because we haven't really done Fourier series of double summations. However, the process for solving for the Fourier series coefficients is exactly the same. Not only that, but when we plug in our initial condition, we'll get a series that we can do the Fourier series, sine series process on. Let's go through and take a look at this. So in terms of putting this up to steps, I say step 1 is the separable case where you get your differential equations. Step 2 is going through and solving the Sturm-Liouville problem for satisfying the boundary conditions. And then step 3 is putting everything together and solving for the coefficients. And we can do that directly because we know that our initial condition is of the form of a function of x and y. And for this infinite summation right here, when t is 0, e to the 0 is 1. So we end up being left with this infinite summation right here. So as long as this sum, this double sum, is uniformly convergent, then we have that this is a valid solution to our problem, because we can do term-by-term differentiation and everything works out perfect. So to solve for these coefficients, a, m, n, we're going to do the exact same thing that we did in 1D, which is do a Fourier sine series expansion of this function f of x, y. And you remember that we do this by considering the inner product, the function inner product of both sides of this expression with some arbitrary element pq. And this gives us an expression of the form f of xy sine of p pi over b times x times sine of q pi over c times y. And on the right hand side we get this exact same expression multiplied by each term in our infinite sum. And as long as this is a uniformly convergent series, we can go through and integrate this term by term. And if we do this, we can take the double integral from 0 to b in x and 0 to c in y. And on the right hand side we get the infinite summation of the double integral of amn, or amn times the double integral from 0 to b, 0 to c of this entire expression right here, dy dx. And one of the things that you want to recall is that if you have a function that's in the form of a product, the double integral of a rectangular domain becomes the product of two single variable integrals. Specifically, this integral right here is going to be nothing more than the product of the integral from 0 to b of sine of m pi over b times x sine of p pi over b times x dx multiplied by the integral from 0 to c of sine of n pi over c times y sine of q pi over c times y. Which are two 1D integrals that we know very well from our orthogonality relations previous. This integral is going to be 0 if m is not equal to p, and the only time it's going to be non-zero is if m is equal to p, in which case it'll be b over 2. Similarly, this integral right here is going to be 0 if n is not equal to q, the only time that it will be non-zero is when n is equal to q, which gives you a value of c over 2. Which means every single term in this infinite sum is 0, except for that one term where m equals p and n equals q, which gives you apq times b over 2 times c over 2, which gives you that apq is going to be 4 over b times c times this double integral right here. Which gives us a direct formula for the coefficients in that infinite sum from before. So the general solution to this problem with these specific boundary conditions is going to be this infinite sum, where AMN is defined by this equation right here. Any MN is defined by this equation right here. And so let's go through and do this for 2 separate examples. First example we'll consider is initial condition fxy being equal to piecewise function that's 0 if xy is not in the rectangle from L over 4 to 3L over 4, or B over 4 to 3B over 4. And y is in the interval, not in the interval from c over 4 to 3c over 4. This is like saying you take an initial square of temperature 1 and every other temperature is 0. And when we do this, we end up getting that AMN the integral for AMN will simplify very nicely. Because if f of x is 0 off of this rectangle, then and 1 on the rectangle, then this integral will become the integral from b over 4 to 3b over 4 and from c over 4 to 3c over 4 with this expression right here. because f is 1, which after an iteration ends up becoming 4 over b times c times 2 times b times sine of m pi over 4 sine of m pi over 2 divided by m times pi times 2c over n times pi times sine of n pi over 4 sine of m or n pi over 2. Where you can go through and simplify this a little bit more, but if you take this and directly go through and verify, we can clearly see that this is the correct solution. So I went in and made some Python code, just like for the 1D case, to visualize this. And sure enough, I'll open that up right now and we'll take a look at it. This right here is a visualization of the sum of the first 100 terms in that series, and 100 terms in M and 100 terms in N. And sure enough, you see that because this is a discontinuous function, you do have some Gibbs phenomena going on at the discontinuous edges initially, but because of the negative exponential, that gets smoothed out very, very quickly. And you see that this animation right here is very clearly showing the correct solution to this heat equation problem. For the values of b and c here, I used value 4 and so 0 to 4 in x and 0 to 5 in y. I encourage you to go through and maybe do another 1 or 2 problems just to make sure that you have the process down. But sure enough, when I went through and did this for another problem, a separate initial condition, just to kind of verify, you get the exact same result. You're always going to have this smoothing effect. The heat equation solution, naturally you expect the temperature distribution to slowly flow out, or the temperature to slowly flow out if the boundary conditions are at a constant temperature here. This is exactly what we're seeing. So another good initial condition to try out, just to make sure that everything's going smoothly. We say f of xy is equal to b minus x times c minus y, which gives you a slightly different integral when you go through and evaluate the coefficients here. We get the integral, the double integral of the function b minus x times c minus y. But this is another relatively straightforward integral to go through and evaluate. And when you do this, you actually get that this is going to simplify down to 4 over b times c times b squared times c squared over m n pi. or just 4bc over m and pi. And this should be m here, and this should be n here, if we're using m and n. So the general solution is the infinite sum from before, with these coefficients plugged in, and I'll actually do that for this one because these coefficients are a little bit shorter for this example. The general solution is 4bc over m times pi. And sure enough, if we plot this out and visualize this, the solution that we get is clearly behaving exactly as we expect. So this is very, very neat. And the last example that I want to show is how to do this for the wave equation in 1D and in 2D.